So our speaker today is professor from here at the department, Mark Piccardo. So Mark has joined the department, he told me, about 2 years ago. So one of the recent acquisitions. He's also at INESC-MN, where he leads a research group. You're also a visiting professor in Harvard, which is very nice. So he started in Torino, went to Paris, to École Normale and Polytechnique, went through other places that I'm not going to mention here. He was awarded the ERC in 2024, and I believe that's the content of that project that you will
A good part.
A good part. I won't say anything about his research because that's his task. And that's it. I hope you enjoy and thank you for accepting.
Thank you so much. Thanks so much, Guilherme. I'm happy to see a lot of you. A lot of faces I remember from my course. So this is an opportunity for me to share a little bit what are the frontiers in our research. I'm happy to be stopped at any time. I know that you tend to be shy, but if someone is brave, feel free to stop me. Okay, starting from the picture, this has nothing to do with my research, but it's a picture I like. So it's a supernova remnant, and I like it because in just one picture it captures two aspects of my research. So really high intensity light, okay, and as you see, this complex spatio-spectral distribution of light. So on completely different time and space scale, we do something like this in our lab, and that's what I'll show you. I wanted to show you, well, this morning I was walking with my son to school and was trying to tell him what I would present today. And so I wanted to explain you a little bit a picture of what I'm doing from a 3-year-old, okay? A biased 3-year-old because he already knows what a laser is, okay? But yeah, he asked me essentially, what do you do? What are you gonna say? And there are two parts in this talk. The first is like some of the superheroes he knows. I try to build really powerful lasers. No problem. Really powerful laser to destroy stuff. Okay. And the second part is quite complicated, but we'll get through this journey. So they have a project in class where they're observing how silkworms evolve into some moths or some kind of butterflies. And so he knows how it's nice to observe nature. And I explained that I'm doing something similar like this, but with light. Okay? Probably this will get you confused, but by the end of the talk, you'll see what I mean. He also asked me why I'm doing these things, which is a very complicated question to answer. I didn't give him this answer, but I can give it to you. You may be familiar with the word ikigai, which is a very interesting word because it's essentially, it highlights a sense of purpose that combines at the intersection of some different spheres. So what you love, what you're good at, what you can be paid for, and what the world needs, okay? And I thought hard how to go in these directions because it's kind of my ikigai, okay? So this was the 3-year-old introduction. Now let's get to the 20 and above, all the serious stuff. So starting from the origin, there is this keyword in the title is structured light, and I want to tell you a little bit what this is. And let's start really from the origin of beam shaping. So humanity has always been fascinated by the possibility of controlling light. And here I'm going back to the first forms of incoherent beam shaping. So even if you look at the Chinese shadow play, so you just play with shadows, right? But you give some structure. And interestingly, today there are research groups that are working with, they call them engineering the dark in photonics. So it's a topic that is coming back in a different form. And the other example I wanted to bring here is a cartoon of a scene of the siege of Syracuse. And so you see ancient Greeks that are attacking Roman ships. How? By essentially acting like human mirror arrays. Okay, so they're redirecting the sunlight and trying to burn the enemy's ships. Okay, now let's jump ahead of several centuries, closer to the modern days. Here you see an example of structured light in some useful applications. So it's called a Fresnel lens. It's kind of a flattened version of a big refractive lens. and it's used, for instance, in lighthouses when you need gigantic lenses. And the last point I wanted to show you on this historical excursus, okay, it's cut here, but here shows the number of papers in laser beam shaping across the years up to the year 2000 or so. And what's interesting, what I want to highlight here is that the laser was invented in 1960 by Maiman, and it took decades before this course started taking off. Okay, it started taking off around the 90s or so. And you may wonder why it took so long for people started to controlling the laser light. And essentially the explanation I can give is based on two types of technology. The first is the holographic technology. We'll see today a little bit in what this can consist. But some examples are spatial light modulators, digital micromirror devices, and things like this. And these only started being available in the late 80s. And the second reason is that to compute holograms, and so how we want to shape light, we need computers that, let's say, in the 60s were not advanced enough. So the combination of these two is what made it possible to do structured light. Now I'm going to go through an excursus of various ways we can control light, starting from the simplest, which is just giving light some space, some spatial structure. What you see here is one of the key technologies to do this, the spatial light modulator, or SLM. You can think of it essentially as some screen where you have many, many pixels, and at each of these pixels you have some liquid crystal molecules inside, and you can apply a voltage difference between two electrodes and reorient the direction of these liquid crystals. And in doing so, you can control locally the phase of a coherent plane wave or whatever type of light that is impinging on this, and therefore start structuring the phase. And something interesting, if you look at this carefully, you see that, okay, here we have a phase controlling device, but what we see here far is the phase of Einstein, right? So an intensity hologram, okay? And this tells already there's some kind of phase amplitude coupling. I can control phase at one plane and get intensity at another plane, okay? We can do this in many ways. One of these is called the Gerber-Saxton algorithms, but it's just an idea or an idea of how already different degrees of freedom of light are coupled. Okay, through this type of devices we can control many different spatial modes of light. These donuts that you see here are called Laguerre-Gaussian modes. These one are Hermite Gaussian modes, and then you can play with their combination and make all these fancy type of modes. And the key things I want to deliver here is that all these complex combinations, complex saturation of light, are essentially given by the interference of many plane waves. Okay, so different waves with different wave vectors. Okay. Okay. Next degree of freedom is the temporal one. Okay, so temporal is structured light, and when you have a train of periodic pulses, you may ask yourself how we can give shape to these light pulses. Okay? And all the idea lies in playing with their underlying frequency components. So there are different constituting colors. Okay? So if I change the superposition in terms of amplitude and phase of all these different colors, I can start shaping, molding these temporal pulses. So there is a deep link between the temporal and the frequency domain by Fourier relation. So in this case, the point I want to highlight is that these pulses are given by the interference of different frequencies, temporal frequencies, not spatial. There was also a Nobel Prize award for the study and development of frequency comps, which are essentially the underlying structure of these pulses. So they are given by all these different teeth in the frequency domain. And frequency comps are super important. They span many different applications, from coherent communications to optical atomic clocks to dual comb spectroscopy. There are just many things. Now there's the last degree of freedom of light I wanted to tell you about is polarization. So polarization is the direction in which the electric field of light oscillates. Okay. And the interesting thing is that we can give structures to this distribution as well. Okay, so we can create simple. They're called vector beams, like this one. So you look at the intensity profile, and maybe you see a donut. But if you look carefully, you'll see that the electric field points in different directions depending on the position in space. And how do we create this? We do this by overlapping two orthogonal polarizations, two distribution of light that are in orthogonal polarization. So if you take this distribution for the horizontal light and this distribution for the vertical light, you put them together, they interfere, and they're going to give you this vector beam. Okay? And we can do not only this simple type of distribution, but more complex morphologies. So they go under various names: spider, web, flower, moonstar, lemon, so on and so forth. And why we're interested in polarization control is because this can give, for instance, super resolution. So if we focus a simple linearly polarized Gaussian beam, we can attain in a region of interest smaller peak intensity than if we focus, for instance, one of these radially polarized beams. Okay? Good. So it was a quick overview of various degrees of freedom. Okay? So we talked about phase, time, frequency, polarization, amplitude. And in my past, I don't know, many years, 10 years or something like that, I've been working on all these different degrees of freedom. So here you see some example from my own research. For instance, in time we developed some soliton generators, and we keep on showing this, in particular on chip. I worked a lot on optical frequency comps. We can make vectorial filters that can make modes of light purer. We work on integrated waveguide to sculpt the amplitude of the electric fields. And finally, I work a lot with what are called vortex beams. I'll tell you in a moment more about what these are in various configurations. So this was done through many different institutions. And something that is in common about these various directions is that I often use to control light. Instead of technology that is established like spatial light modulators, I used an advanced type of material that are called metasurfaces or metamaterials. Okay? And for those of you that don't know about this, I'm going to give you a very quick introduction, just a few slides, so to explain what these are. Okay, what is a metamaterial? The typical definition is that these are artificially structured materials with which we can control many different waves. So not only light, as in my work, but also sound, even vibrating waves, etc. And the key thing, what is really defining the metamaterial, by the way, meta means going beyond, and beyond what? Beyond the properties of the bulk material. The key thing that defines a metamaterial, the fact that they are assembled by subwavelength structures. Okay, in the case of light, they are nanostructures, but for other waves, as long as they are smaller than the wavelength. And for instance, in the world of photonics, with metamaterials, we can open up really curious and unconventional effects. For instance, we can make negative index materials where the phase velocity appears to be negative. And if you look at refraction, this is just a cartoon or artist view, let's say. But if your water here would be, instead of if your liquid here instead of water would be a metamaterial with negative index, you will see anomalous refraction. Okay? And another type of effect we can have is near index metamaterial. In this case, the index is not negative, it's near zero. And the flow of light inside the material is almost like a DC wave, okay? Almost like static electricity. So all these are weird effects. There is, however, complexity in working with three-dimensional metamaterials. Is the fact that, well, they're first of all very difficult to do because you need not only one layer but many. And the second, often they rely on resonance, and so they are not very efficient. So some people demonstrated, for instance, invisibility cloaking, but it always remained at the proof of concept. Okay? What really brought the field of metamaterials towards mainstream, I would say, and really applications in real life, is that of the category or subfield of metasurfaces. So these are metamaterials but planar, okay? Where again we can think of every independent subwavelength structures as small antennas or small waveguides that can locally control the light. Okay? The advantage of metasurfaces is that since they're planar, we can use planar technology to make them. And also they have very little losses because they're extremely thin. Okay? So typically in the visible, we work with metasurfaces that are of the order of less than 1 micron. Okay. So how does a metasurface work? This is just a simple intuition. You can understand this using Huygens principle. So you have plane waves that are impinging on these arrays of nanoscatterers. And then each of these elements, which we can see as a small nanopillar, again, with subwavelength dimensions, redirects, creates a secondary wavelet, and then the interference of all these wavelets redirects the light. Okay? We can design the actual light scattering that occurs on nanopillars can rely on different phenomena. Can be resonant or non-resonant. I won't explain you here the details, but just want to mention that there can be different ways we can control the light at this scale. And this is the most intuitive picture. There are advanced metasurfaces today. So there's a topic that has been really, really hot in the last 10 years. So there are metasurfaces that can have nonlinear frequency conversions. Metasurfaces that are non-local in the sense that they can control information, for instance, response, rather than having a spatial local response, they can respond to frequencies. And we can also design metasurfaces rather than just with single nanopillars, we can do inverse design. So we set a certain goal, a certain figure of merit, and we just try to optimize for a dielectric distribution that does that function. Okay? So for instance, what you see here is a demultiplexer. So you come in this channel with 2 colors, and you want in this tiny structure to split out these colors. Okay? So it's like a grating that is very, very small. Okay, there are 2 points normally I like to highlight about metasurfaces. The first is the fact that today we can really make large ones, which is different from what we can do with metamaterials. So we are seeing here is my former mentor in Harvard, Federico Capasso, who boosted this field. And is right next to a metasurface that has 10 centimeter diameter. Okay, so there are tens of billions of nanoelements here, and we can do this today. So it's expensive. Like, can you guess how much is a metasurface like this? Nobody will say anything. Like anyone, any value.
100,000 euros.
Very close. Yeah, very close. Very good. This one in particular was 80K. Yes. So they come at a cost, but it's possible to do them. Okay. Another thing I want to highlight is that they are being mass produced. Okay. There's a spin-off company actually from Harvard. It's called MetaLens. And these days already, if you have one of the latest iPhones or Samsung or even iPads, inside you have metasurfaces. So they're being mass produced. And why? Because, well, they're thinner than conventional elements. They rely on refractive lenses. And also they're much more functional because instead of just relying on the curvature of the element, we can engineer the single nanopillars, and therefore we can typically achieve different functionality or higher performance. And the last point that I find really unique about metasurfaces is the control of polarization. So what you see here is a crystal that was thought to be used, so there are theories that were thought to be used by the Vikings to find the sun position in a cloudy sky. So the way it would work, this is a bulk birefringent crystal, and so the way it would work, you would see 2 images, 2 slightly different light distribution when you look at the cloudy sky, unless the source, so the sun, is oriented along the optical axis of this birefringent crystal. And so then by trying to reduce the splitting of these 2 images, you could identify with I think an accuracy of less than 2 degrees where the sun is in the sky, which would be enough to orient for the sailing. But anyway, this relies on bulk birefringence. And what's cool about metasurface is that we can have a different type of birefringence that relies only on shaping, on the nanostructure, okay? Nanostructure shape. So we can take a material that is non-birefringent. Non-birefringence means that regardless of the polarization you send, you're going to have always the same phase in transmission. For instance, fused silica, which is a type of glass. And if you use it in bulk form, there's no change in terms of polarization. But if you start nanostructuring with these anisotropic elements, so for instance, doing these rectangular elements or elliptical elements, you can start having an independent control of polarization. Okay? Really cool because it comes all from the nanoengineering. So all these, the next point I wanted to highlight is that we are getting to a new paradigm of structural light, and this is something hot and hot in the field. And the idea is to start combining different degrees of freedom. So not anymore just structure the amplitude, not anymore just structure the frequency, but start making correlation. And this is very interesting. I've been actually one of the actors in the community, among many others, that started driving this change. And I think really that putting together more degrees of freedom, there's much more we can unlock from light. One of the hottest combination of degrees of freedom is space and time. So we're talking today a lot about spatiotemporal photonics, and it's about the simultaneous control of these 2 degrees of freedom. And I wanted to give you a quick example from my own research about space-time. So what you see here is an idea, and the idea was, can we take a light source that have many different frequencies? So the optical frequency comb I mentioned you just a moment ago. And can we do it in such a way that a different frequency will have a different spatial mode, okay? And the spatial modes we're working on with, in this case, are called optical vortices. So all you need to know is that we create this by sending a Gaussian beam through a plate that has a phase singularity. And at the output, we get, instead of having a planar wavefront, we get a wavefront that is like in a corkscrew. So it has a twist. And we say that this carries orbital angular momentum. And the cool thing is that we can have a whole set of vortex modes depending on how many phase singularity, how many phase gradients we have here. So here you see just one. It goes from 0 to 2 pi in phase. But we can do it with 3, 5, as many as you want. Okay? So the idea was, can we create a spatiospectral correlation when different frequencies are associated with different vortex modes? How do we do this? And what happens if we can manage to do it? So the way we did it is the following one. We send essentially an ultra-short pulse, which you can think of as a white light bullet. So white light in the sense that it has many colors, and bullet because it's a very short pulse. Okay? And we throw this against a type of holographic element that is called the diffractive multilevel axicon. And in the far field of this element, we are splitting all the colors of the bullet into concentric rings. Okay? So you'll have an inner ring that is green, then yellow, then red, and so on. And then at this specific plane, if you place a tailored hologram so that the green will see a certain azimuthal gradient, the yellow another, and the red yet another one, you can create this correlation. Okay? And then once you recombine this beam, you create what's called a light spring. Okay? Which is a pulse that is not anymore propagating like a bullet, but has this helical intensity profile. So the way we do it is rather complicated. I will skip the details. But in essence, we can create this and then characterize it by measuring at many different colors the intensity and phase of this beam. And then if we analyze this spatiospectral information, we can reconstruct experimentally the correlation between the topological charge of these vortices, remember is the number of azimuthal phase gradients that are in the phase, versus frequency. So in this case it's just linear. And then once we have this information, we can just do an inverse Fourier transform and really visualize how our space-time beam is in real space. So what you see here, the cross-section is space, and this is time on a femtosecond scale, and it has this helical structure. This means that if you propagate this against a perpendicular plane and you observe what's happening at that plane, you will see a pulse that rotates in time on a very, very short time scale, femtosecond time scale. And it's very different from what you would get if all the frequency had the same topological charge. So imagine the correlation here was horizontal. You would just get a pulse vortex, which in terms of iso surface would look like a torus instead of this helical structure. Now we can also do light springs at Técnico. So this was prior work I did in Italy. So we were able to reconstruct this type of experiments here. And I'm pretty excited because one of the next things we'd like to do is try to send these light springs into laser matter interactions and try into basically a nonlinear medium, and try by laser matter interaction create new frequency, new emission frequencies by driving a response in the material from these pulses. And then what we want in particular to do is try to control the orbital velocity of these pulses and then try to see the radiation that comes out. Okay, this drives me to the first big frontier, which is, I present here as a question. So can we bring the advanced structural light to the high power regime? So I showed you that we can do a lot of things in structuration and control of light, but most of these things, like 3-dimensional structural light, even 4-dimensional structural light with time, are at moderate power levels. And my vision here was try to bring this manipulation and control of light at really high intensity, for this to become a new knob to control matter. Okay? And I'll tell you in a moment what we want to do with all this. So this is just an overview, state of the art of several intense laser matter interaction today. People can do interesting things like attosecond pulses that spread out azimutally like in a lighthouse, holograms that are made of plasma, space-time beam that look like a focus that is flying. Okay? But apart from the details here, what I want to highlight is that most of these applications, they still rely on conventional optics. So simple prisms, simple diffractive optical elements, or chromatic lenses and things like this. And so the whole idea is, what can we do if we start bringing in more advanced control of light? So the idea that I had in mind was trying to develop a new class of metasurfaces, meta-optics, that would work at these extreme powers. So we can then start shaping light at very intense power levels. There are many requirements to overcome to do all this. The material needs to be high power compatible. We need to have a full phase control, which is kind of a contradiction with this high power compatibility. We need to make them large. We need to make them broadband, because when you use intense light, typically you work with ultra short pulses. And ultra short pulses have many colors, and so you need to tailor the response at many colors. So all these things are very challenging, but that's a little bit the vision and where I wanted to go. So this entire frontier goes along the developing high intensity metasurfaces for structured laser matter interactions. So the idea here, instead of driving the laser matter interaction with a simple Gaussian, a simple distribution of light, let's try to drive it with more complex light. So the ingredients here are high power laser that nowadays are available in the world. Try to combine this with this structural light zoo that is that today we can have at least at low power. And then it can go in many different directions. So when I moved here to Técnico, something that got me really fascinated is all the work that's been done on laser plasma interactions. And so naturally, by interacting here with several groups, we started developing an idea of using this to control laser plasma instabilities, which are super important because are one of the barriers towards fusion, which, as you know, is one of the main provisions to have essentially clean, free energy. Other things that can be done with this is to structure laser plasma accelerators. So in a laser plasma accelerator, you can accelerate particles by sending a ultra-fast, ultra-short pulse. And even beyond this, I think that we can drive any type of nonlinear process using this type of pulses. So I'm gonna go fast on some of these, but why now? I mentioned already the field of metasurface is mature. We can mass produce them. We can make them large, which is essential if you want to have a high power beam, because to reduce the intensity on the material before damaging, you want to expand it as much as possible. This is why I highlighted before the fact that we can do 10 centimeter devices. We have high power laser available. Actually, I have a collaboration with Eli, they just started, which is the extreme light infrastructure. So I have the world's most powerful lasers. And it's really timely in terms of particular laser plasma advances, because one of the decadal challenges there is that we must master the art of molding plasmas with lasers, which is really one of the things we want to do. So there is a gap between these different fields. They go from high power laser to nanophotonics to plasma physics. And with this new development, we're trying to put together this intersection and expand this intersection. So what are we doing in particular? We started, since the very beginning, I figured out that we would need to bet on a material that is very robust. And so differently from what people in metasurface normally work on, which are metasurfaces with different material for the nanopillars and the substrate. Typically, people use nanopillars with high refractive index and a substrate that is glass. I thought that having this interface would not be good for high power, because once you have an interface, the nanopillars can just get damaged. And so we started sculpting our meta-optics out of the same block of glass, which is very nice in terms of robustness, but very challenging in terms of light control, because silica as a glass has a low refractive index, and so it's hard to confine light in these structures. So one of the first things we figure out is that we will need really tall vertical nanopillars in order to have a full control of the light. What I mean with full control, when we make these metasurfaces, we try to figure out some nanostructure, nanoelements that can, depending on geometry of the nanostructure, we want to have a phase shift that goes from 0 to 2 pi. Okay? So we say that we have a full phase library when we have enough elements, enough nano elements that can give me any possible phase delay. And if you try to do this with a short glass nanopillar, you see that the phase you cover only goes from 0 to approximately pi half. And the only way to go there is to have really tall nanopillars, which were thought to be impossible a few years ago, but with the development we did at INESC-MN in the clean room just across the street, now we can make them with the exceptional aspect ratio. So they are 14:1 aspect ratio. So you can think of these as like skyscrapers at the nanoscale. And now we are pushing this even further, even beyond 3 micron. We're trying to do 5 micron tall nanostructures. We proved that these devices are robust, so they basically withstand a damage threshold that is really close to that of bare silica, which is one of the most robust materials for ultra-short pulses. And then we use this to demonstrate a variety of structural light, but now also compatible for high-power lasers. So here you see an example of making a vortex beam, one of these vortex beams. This with a topological charge of 5, as you see from the number azimuthal gradients here. And then we developed this also to make polarization wave plates. So a wave plate is something that is used to turn or change the input polarization of light. And it's very important for high-power lasers. And we show that with these glass meta-optics, we can do this as well. I'm also excited about the fact that now what I showed you were basically results from a first generation of devices. And now we have been working on a new generation that is very, very promising. So what we changed, essentially the reason why I'm most excited about this is because of the following. So what you see here is what happens in the lab when we send red light on one of these metasurfaces. Supposedly in this metasurface, we should create a vortex that looks like a donut and deflect it at an angle. Okay? So if it's very, very efficient, you should just see a vortex slightly off axis. But in the first generation, the efficiency was around 70 or less %, and therefore we still had a very strong zero order. So a lot of light was not modulated from the laser. And what we did, and also the second thing is that the devices were relatively small. They were only 100 micron in diameter, and therefore the pulse energy, the maximum pulse energy we could address with this was 50 microjoule. Above this value, we will start damaging the devices. And now we've been working on a new generation, so we improved the design, we improved the EBL patterning, we managed to make a larger area file, just a compression issue. And what you see now these are preliminary results from the new devices, which now are seen by naked eye because they're 1 millimeter. They can withstand 5 millijoule, which is already a high pulse energy. So most high-power lasers, they're like Titai Sapphire that are in academia, they're around these levels. And in particular, we basically don't see the zero order anymore. So it's really, really weak. It's super important because for this to become a product, it's really required by all these big laser facilities in the world that these are as efficient as possible. They put a lot of effort in trying to maximize the laser energy and they don't want to waste it because of a plate that is not efficient. So this is very interesting. I'm thinking that maybe in a few years there could be a company starting out of this, so you could make a spin-off. So if you're interested, just let me know. We have new lab equipment, so all this was funded by an ERC starting grant that gave a good boost to my lab. And two biggest pieces of equipment we bought is a lithography machine to grayscale. So here we can control really multiple levels in a dielectric. And the other thing is a high-energy ultrafast laser to be used for all this research. As I mentioned, the various applications that go here can be in many different directions. So not only understanding laser plasma instabilities, but also nonlinear frequency generation. We can use this high-power laser to do material processing and many other things that are just being, I think, at the edge of what we can do. We are going towards application. I wanted to highlight also a recent review I developed with some of the world experts in laser matter interactions. So these are from Técnico as well, but also ELI, the Streamlight Infrastructure, Laboratory for Laser Energetics in Rochester, UCSD, Laboratorio d'Optique Appliquée in Paris, and the Weizmann. So these are all leaders in the field. And I'm very happy about this because we start finding synergy about the structural light we can bring and the laser matter interaction experiment they have. Okay, now we take a big breath and we go to the second and last part, which started to me kind of a curiosity. So I was really keen on structural light and I started wondering what is really the ultimate limit of structuration of light. So most of the examples I showed you, they rely on top-down structural light. Top-down means that I know what I want to get, and I just figure out the profile that I need on my SLM or the structuration of the material I need to get that hologram. Okay? But the question I want to ask here is, would it be possible to have a configuration which light structure itself? So I'm not telling light what to do, light figures it out on its own. You may ask why, but yeah, it's a good question. We'll get there. And so if we assume that you want to go there, definitely there are some key ingredients that we need. The first is that we need interactions. If you just throw light in free space, not much interesting can happen. Okay, it's just linear transformations. Second thing, we need advanced transformation, so something complex. And the last thing is probably we need iteration to have something that's keep on evolving and have something interesting. So what I'm picturing here is trying to figure out a laser that inside in which the light starts evolving and eventually start getting form as some kind of artificial life. So I want some forms of light that can evolve, reproduce, disappear, and do really complex type of operations. So let's assume this, we want to do this. How can we go in that direction? Okay. So we need to go through the various elements, and the first is interactions. Okay. So how can we implement a system in which we manipulate interactions? We need some kind of nonlinear structural light, which is a very interesting concept. However, when we look at most of the studies that people have done, they typically convert the frequencies. So for instance, here you see a nonlinear meta lens. A meta lens is a metasurface acting like a flat lens. And what happens is that when it acts like a regular lens at the design frequency, it focuses at a certain distance, and when we send more intense light, it can convert the frequency and then focus at a different place. Okay? Other type of metasurfaces that are nonlinear that people have demonstrated, for instance, these are called Janus metasurfaces. So are metasurfaces that depending on the side we illuminate them, they give different holograms, completely independent holograms. And there are other studies in nonlinear structural light, but they all rely on frequency conversions. And I don't like this for my purpose because if the light is converted, I cannot really iterate, right? I go once through the device, the frequency changes, and then, yeah, I cannot keep on changing the frequency forever. It will just not go really far. So we need to change that somehow. And the other thing is, how do we implement advanced transformation? So what I showed you is most of the example I showed you rely on a single layer transformation. Okay, so I have some kind of plate, I send light through it, and I change its mode. However, it's quite interesting what happens if I can have multiple layers. People refer to this with different names. One of these is multiplane light conversion. And you can think that having multiple layers gives you more degrees of freedom, and so you can do more transformations in parallel. So for instance, you can have like here like 7 layers, have various input modes that are spatially separated, and each of these is mapped to a different output modes. Okay. But maybe the most advanced way to do a transformation is that of having multiple layers and then an activation function, so a nonlinear layer. And these are really cool concepts. They're called optical neural networks. And you can think of these as a physical version of the artificial neural networks that you have heard a lot about, right? So here the various layers are actually can be diffractive layers or some interferometric layers, but they all manipulate light. So they're not electronic neural network running on our computer. They directly manipulate light. And we can do things really similar to what electronic neural networks do. For instance, we can do the classification. So, you know, a typical test for a neural network is having the MNIST dataset, so all these handwritten numbers, and then the neural network can classify. And we can do the same thing with light. So this is very interesting because you can do very advanced transformations. Now there is a catch. The difficult part in optical neural networks is that it's not the hidden layers, the linear part. With light we can do really well. The very difficult thing is the nonlinearity, so the activation function. Typically nonlinear effects with light are a pain. And so the approaches that exist here go typically in 2 directions. One is optoelectronic hybrid neural networks. And so what people do, they do the propagation to various layers of light, and then they do an electronic conversion. So there is a camera, and then electronically they can process the signal. Okay? Or they use other methods like these data repetition methods, but they all require electronic encoding. And the other approach that is the one I'm more interested in is one where it's all optical. So also the nonlinearity, I want it to be optical. Okay? Why? Because in my dream, right, of that strange machine, I want this light to keep on iterating all optically really fast. Okay. So there are various ways that people are trying to implement all optical nonlinearity. Some require cold atoms, which are very complicated setups, and the nonlinearity is also not very strong. Others are called image intensifier, but they're relatively slow. So the one I'm most interested about relies on nonlinear effects that are instantaneous, like the Kerr nonlinearity. The only disadvantage here is that you need typically an intense laser, because these nonlinear effects are only triggered at high power. But we work with high power lasers, so it's perfect for us. So this is the type of nonlinearity mainly we work with. And before starting and trying to do that complex artificial light scenario, what we started as research actually last year with a master student here from Técnico, I tried to figure out what would be the simplest problem we could try to tackle that would not be possible to do with what is existing. And we frame it this way. We call it an AND gate. It's a simplified version of an AND gate with light. So the idea is that think of it as a black box now, and you have at the input, you can have 3 possible configurations. So you can have mode 1, mode 2, or the 2 modes at the same time. And at the outputs, you want 3 different channels. Okay? So you want to distinguish these 3 cases. And you see right away that with a linear system, you cannot do much, right? Because with mode 1, you're going to get something. With mode 2, you're going to get another thing. And with the 2 modes together, you're going to get some kind of interference, right? But you cannot distinguish the 3rd mode as a completely independent, distinct mode. So linear optics by itself cannot go any far. So we had to figure out how to design a nonlinear optical system that could do this. Essentially, we had to figure out how to make an all-optical nonlinear neural network. So what we have in our system are multiple diffractive layers, then a nonlinear layer. So a layer, it means that it's a layer that gives a phase, but the phase depends on the intensity, and this is fundamentally nonlinear. We also had the problem of how to train this system. So how can we figure out the hologram we need to put, the linear hologram we need to put in this system in order to achieve our goal? And this was really also very nice that the student that I had last year, she had a minor in AI, so she was very good in doing all this type of optimization. So we ran the optimization. This took quite a while, but in the end we got really happy because it showed already, at least in simulations, it's possible with this type of system. So it's an optical architecture I won't go into details, but it has some nonlinear layer and some linear layer. We can achieve much better classification than a simple linear layer. Okay. So this was a good, encouraging results from last year, and now with a new student, she was very determined in doing the experiments. They were very challenging, but great, she had the drive. So we're now trying to implement this. The very first thing is try to find a nonlinear material that has strong nonlinearity to avoid going to really high power. And so we're building now what's called a Z-scan experiment. It's an experiment that allows us to plug in many different materials and a structured nonlinearity. And then the next step, we're about to do it, so in 1 or 2 months we'll know, hopefully, whether this works or not, is to implement the AND gate that I just showed you with an optical system. And I'm very excited for this to work, because as soon as we can demonstrate that this AND gate works, we have the basic pillars to make some nonlinear optical transformation. And my vision in this is going towards artificial photonic life. So I'm inspired by a Google project that is called Linea, just runs on computers, okay? And so this is essentially a continuous version of Conway's game of life. I'm going to show you in a second, in the next slide, what this is. But the output of this is that you just give in some simple rules, and you can see very complex evolutions of these lifelike entities. Okay, you can almost look at what's going on here with the eyes of a biologist. Okay, you have all these structures that emerge. They interact. You see, sometimes they split, they replicate, they evolve, they die, and it's just very, very fascinating. Okay? So what's at the core of all this? The core of all this is a cellular automata. So this is a concept that was introduced by von Neumann, and he proposed it essentially as initially with his self-replicating universal constructor. So it's a set of rules, local rules, that allow to create a machine that replicates itself and then basically constructs another machine that constructs another, and so on. In the easiest form to grasp, cellular automata are very, very simple. You can just think of these as imagine a one-dimensional arrays with boxes that are black or white, so 0 or 1s, and then you define a local rules that couples a neighborhood. So the smallest neighborhood, you can think like three cells, and you have to write the rule set that says, okay, if I have black, black, white, the next will be black. Okay, and you just write all the rule sets, so these 8 possible evolutions, and then once you run it in parallel for the entire array, you start having these very fascinating patterns that appear. And it's very beautiful because it comes from such simple rules. This is a lecture I attended some years ago in Harvard by Stephen Wolfram, which is the Wolfram of Mathematica, the tool that many of you use. That was really fascinating. This book, okay, some people considering it a little bit too much, going too far-fetched, but still I find it very inspirational. I recommend you. It's free. You can go online, look at it. A new kind of science. Anyway, one of the efforts of Stephen Wolfram was trying to classify all the various cellular automata that can evolve depending on different rules. So you can have some classes that are just uniform, so boring. Some are repetitive, also quite boring. Some are random. I would call them weird. And then complex are the most interesting ones. Okay. And why this is interesting? Because, well, it gives a feeling that there is something really fundamental in what surrounds us. If you start looking at two-dimensional forms of cellular automata, you start getting structures that are very similar to crystal snowflakes. It can mimic the dynamics of fractures, reproduce patterns that we see everywhere around in nature, and all this from these super simple rules. So if you think about it for a moment, I think you will find it really surprising. And Conway's game of life is a two-dimensional version of this cellular automata I mentioned before. So in 2D, your neighborhood is not just 2 cells, but all the cells around, right? Again, you define a rule, and what you can get is, well, these very complex structures, these are called gliders, and there's a whole taxonomy about this, so people have been studying this for long. And in Linea, okay, in Linea, essentially, in this Google project, essentially is a continuous version of this. And why I like continuous? Because optics is continuous, right? So that's the hidden link. Another thing that is interesting, okay, these are some different attempts to start implementing cellular automata as with optics. Okay, starting from Bell Labs in the 80s, mainly for optical computing, something that still a very hot topic, but I don't know when, if ever, will take off. And more recently, people started looking at these elementary cellular automata with light. Another important thing here is that there is a deep link between cellular automata and deep recurrent convolutional neural network, which is essentially why I find interesting that we can make an optical neural network to implement a cellular automata-like system. And here is a little bit my vision, what we're working on at the moment. So inspired by this optical linea, as I mentioned, we are now working on the simplest building block of a nonlinear neural network, but then I would like to eventually make this strange laser that will almost look like a microscope to look at this artificial life. And one of my students just got a Fulbright grant to continue this with our collaborators in Yale. So I'm very happy about this. By the way, I think she's the last one getting a Fulbright because Trump, the day after, closed the program. But it seems they invited her to start the process for the visa, so I hope she can still go. Okay. And with this, I'm closing. I want to give you final perspective and brief summary. So I showed you two frontiers of light shaping. I believe these are world-changing directions. At least they are my motivation to go forward. One is high-power structural laser-matter interaction, and it associated with it there is a decadal problem in plasma science engineering, which is we must master the art of molding plasma with lasers. And if this will ever work, and it's a huge if, one day structural light could be powering the world, which is still an amazing horizon to look at. And the other direction I showed you is nonlinear transformation with structural light. The decadal problem associated with it is in artificial life, and is essentially whether we can find novel living organizations that can form. And the way I look at this, as I mentioned, is kind of a strange laser microscope to look at artificial life. I want to close, thanking all the people in my group. We are the multimode photonics laboratory. So we work with all these different degrees of freedom. Here is our website. In particular, we thrive at the interface between laser and structural light. And there are always several projects, so pick one and pick two. So here is my slide of advertisement. So if you are considering doing a project, get in touch with me. And with this, I'm done. Thank you very much for the attention.